Get your pointer ready on your slide.
Stop talking. It is.
Okay, here we go. Good afternoon, everyone, and welcome to the 25th Hubert M. James Lecture. The James Lecture is named for Hubert M. James, a native of West Virginia, who provided outstanding service to Purdue physics and astronomy from 1936 to 1974. His Harvard PhD research area was the application of quantum mechanics to single molecules, and he continued his work in quantum mechanics applied to multiple problems throughout his career. During World War II, he worked on developing radar at the MIT Radiation Laboratory. Professor James served as department head from 1958 to 1966. The lecture series was endowed by his family in his memory in 1986 with the goal of highlighting fundamental aspects of physics for a broad university audience. Past speakers in this series include Norman Ramsey, the inaugural presenter, Fred Reines, C.N. Yang, Leon Letterman, Freeman Dyson, Frank Wilczek, Theodore Honch, Andrea Ghez, and most recently, Barry Barish. Today's presenter is Sara Seager from MIT, and I will turn it over to David Koltik to introduce the speaker.
Thank you very much, John. Just before we get started, those of you who are on the YouTube, during the lecture, you can ask questions through the chat, which will be discussed with Professor Sara Seager at the end of her presentation. Let me just start by saying it's a great honor to introduce Purdue University's Department of Physics and Astronomy 2021 Hubert James Lecturer, Professor Sara Seager. When Professor Seager's nomination came before the Hubert James Committee, there was no question of Sara's incredible contribution to science through innovative research, scholarly publications, and beyond this legacy, her extensive popular writings discussing science of exoplanets. But beyond this, there's a very personal human experience of being a woman scientist described in her latest popular book, The Smallest Lights in the Universe. Her present discovery and exploration work include the MIT NASA team mission TESS, or Transiting Exoplanet Survey Satellite mission, the JPL MIT Astrea, or ARC Second Space Telescope Enabling Research in Astrophysics, and the Starshade Rendezvous mission. Professor Sara's honors and awards are numerous. She's a member of the National Academy of Science, the American Academy of Arts and Sciences, a MacArthur Fellow. These are just mentioning a few of her honors. Sara is a joint citizen of both the United States and Canada, and she has recently received one of Canada's highest civilian honors, being named an Officer of the Order of Canada. I'll read a short excerpt from this high honor because it encapsulates very well Professor Sara Seager. As a planetary scientist and astrophysicist, Professor Seager is at the forefront of exoplanet research. When Sara began her graduate studies at Harvard in the mid-90s, extrasolar planetary research was an emerging field, largely based on theory. However, her cutting-edge work on the planetary atmospheres, planetary interiors, and exoplanet transits have led to numerous firsts for this little-known field and helped to launch it into existence. Her current research uses theoretical models to examine in detail exoplanet atmospheres, their internal structure and composition, and potential habitable zones, and gaseous signatures indicating life. Of course, there's much more to be said about Professor Sara Seager, but the physics department at Purdue University is greatly honored to present our Hubert James Lecture for 2021, Professor Sara Seager of MIT. Sara?
Thank you. Thanks, everybody. It's a pleasure to be here speaking to all of you, and I'm here to tell you about exoplanets and the search for atmospheric biosignature gases. A few billion years ago, the humble bacteria, cyanobacteria, discovered photosynthesis and eventually re-engineered our atmosphere to fill it with oxygen. Without vegetation, without plants and photosynthetic bacteria, Earth's atmosphere would have virtually no oxygen. And when I love to think about the stars and any planets that might be orbiting those stars, if there happen to be some intelligent aliens with the kind of telescopes we are building, if they look back at Earth, they'll see oxygen. And they'll be highly suspicious because oxygen is an incredibly reactive gas and shouldn't be in our atmosphere. And if they can have telescopes to find oxygen in our atmosphere, they'll probably be fighting over data analysis and really kind of arguing about the source of oxygen. But it should be a huge indicator that something on our planet is up. And hopefully they can associate it with life. So what I'm here to talk about today is I'll introduce biosignature gases. Then I'm going to spend some time talking about phosphine on Venus. Then I'll spend about a third of my talk on the search for life on exoplanets. So a number of years ago, I came across this quote: "Nothing would be more tragic in the exploration of space than to encounter alien life and fail to recognize it." And this came out of a report. You can actually download this for free. And it was really more about our own solar system. But I've carried this quote with me as a kind of guiding principle, because our own Earth has had significant atmospheric oxygen for the past billion years, which is not its whole life, right? Earth has been around for 4.5 billion years or so. And so, our Earth was not fully oxygenated. So I always wonder what kind of gases might be produced by life on another world. And in one of my meetings today, I met with Professor Stephanie Olson, and I'm excited to learn what she finds in terms of why it took Earth so long after we think life first started producing oxygen for our atmosphere to fill with oxygen to 20% by volume. But about this question about what kind of gases might be produced by life on another world, it's kind of really an interesting question because life on Earth produces so many gases. Thousands of gases, actually. And in fact, if we think about our own Earth's atmosphere, there's this amazing kind of factoid that every gas in Earth's atmosphere to the part per trillion level, with the exception of the noble gases, the gases in our atmosphere to the part per trillion level are actually all produced by life. Although most of them have a dominant source that is not life. And this includes gases like nitrogen, of course, carbon dioxide. We humans breathe out carbon dioxide. Gases, even like ozone, apparently is produced inside some cells. So thinking about all of this, I got a bit tangled actually into what I call a crazy theory. Now, if I was with you in the room, I would ask you, how many of you receive emails about crazy theories? I bet you, if you were there, you'd be smiling. If I was with you in the room, you'd probably be smiling because physicists get lots of these emails. I'm probably sure all scientists do, but weekly, almost sometimes daily basis, people want to share their theories. But my theory, by the way, was a bit crazy, and it was that perhaps life on Earth produces every single molecule that could be in gas form. And I, for some reason, wanted to know the answer, whether this was true or not. And so I recruited a couple of my biochemistry colleagues and asked if they would help me sort through this problem. And then you have to ask, well, who does the professor go to with the crazy theory? If everyone's always coming to us, I had to go to the next level up to a Nobel laureate. And there was one who's a friend of astrobiology, and my two biochemistry colleagues and I, we had worked out this theory and had a list of gases. And we went to the Nobel laureate, and he crushed the theory by immediately finding a counterexample a small molecule that is not made by life. But the long and the short of it is making like a basically 6 or 7 year story into half a minute. We ended up constructing a couple of different databases. One of them has, to our knowledge, all molecules that are in gas form at Earth's, at like a habitable planet's temperature and pressure. And another one actually is all the compounds, gases, molecules, solids produced by life on Earth. We were able to find an answer to my question, which is that about a quarter of all gases are made by life on Earth, but it ended up being like the wrong question to ask. Nevertheless, we now have this comprehensive database, and it's illustrated here by this sea of molecules that we call in so-called chemical space in the background. And this set of molecules gets filtered by our computer algorithms, illustrated here by this shaker filter. And this is showing you that 3 streams, 2 of the streams go near a planet, illustrating our hope that we can hopefully identify some molecules, gas form on exoplanets that might indicate life. And one of the streams on the left of this picture here actually are molecules that we found, or fragments of molecules that are literally almost never or incredibly rarely made by life. And my team now ended up working in chemoinformatics, trying to understand what we have found. But back to sort of a biosignature gas, which is a gas made by life that can accumulate in a planet atmosphere. We now are trying to go through this list of gases exhaustively. And I'm going to walk you through it with this, what I call triage for thousands of gases. And this figure comes out of a PhD thesis for my student, Zhucheng Zhen, who actually just completed his PhD a few weeks ago. What you're seeing here is that we start with this database. We call it our all small molecules database. And this is a triage phase. And then we ask, do these gas or class of gases of interest have any spectra, molecular line list cross sections? And usually they don't, by the way. I was just remembering that one of the gases, we borrowed some of Professor Dan Sitsko's equipment when he was at MIT to try to measure the cross sections or of one of the gases. It's quite hard, actually, we found out. But only about several hundred of the gases out of the many thousands we're interested in have measured spectra. Then we take the gases and pump them through a so-called spectral simulator to see that if they were in an exoplanet atmosphere far away, could we detect the gas? Would the gas be distinguishable, from other gases that might have a similar spectral fingerprint? Long story short, if the molecule passes this triage phase, then we get into a more heavy-duty set of simulations involving atmospheric chemistry and specifically photochemistry. Because gases, that come out of our volcanoes or that are produced by life, many of them just get destroyed, almost instantly by ultraviolet photons from the sun or by OH radicals in our atmosphere that destroy the gases. So we kind of work through all this, and if the gas passes through the tests, I then usually assign it to a student or a postdoc who works on a gas or a class of gases to see whether or not it might be a good potential biosignature gas. It might be produced by life on Earth, or perhaps it's a gas that's rarely made by volcanoes or other non-life processes, which is also a win. Now, I sometimes get asked, am I expecting to find like a brand new amazing gas? Like, not necessarily. We're just kind of trying to do this. So like the quote I started with, that we don't miss anything that might have been obvious. So working through this whole triage process, and also the other line of research I touched on, where some gases appear to be rarely or never made by life, we came across a really interesting gas. And this gas is called phosphine. Phosphine, well, phosphorus is an essential element for all life on Earth. And here on Earth, by the way, there's almost no phosphine because we don't have any hydrogen. We have very little hydrogen. So phosphorus is in the form of phosphates. And it turns out that phosphine is very thermodynamically disfavored. That even if you had a bit of hydrogen lying around, the phosphorus would not want to combine with phosphine. It's very, very hard to, the temperatures and pressures have to be much, much higher than are here at Earth's surface to make phosphine, even if we did have hydrogen. And also phosphine does appear to be completely absent from biology. And so initially, people didn't like the idea of phosphine as a biosignature gas. Indeed, it has no confirmed life-producing instances, and phosphine is very toxic and unstable. It was used as a chemical warfare agent in World War I. But it turns out that phosphine is toxic and unstable only in oxidized environments. And although we don't yet know, biologists don't yet know about the actual pathway to phosphine production inside life, they don't know what enzyme helps make phosphine, there is very, very strong evidence for phosphine in biological systems, like in laboratory cultures of mixed bacteria, phosphine has been measured there. And it's also found in wetlands, in oxygen-free environments. It's also found in animal guts. In fact, there's this paper about that there's a lot of phosphine over a penguin colony, penguin poop. So phosphine is a gas that really became of interest to us, and we put it through our exoplanet atmosphere models. And I'll be coming back to that a bit later. But in the meantime, I wanted to share with you the story about phosphine on Venus, to tell you a bit about where that came from and where it's going. So while my group was working on phosphine, totally independently, a group across the world, led by Professor Jane Greaves at Cardiff University, UK, was working on phosphine. Now, this is a very unusual story, and I know that a lot of us became scientists because we like to explore, we're curious. But how often do we really go out on a limb and try something way out there? Like, not too often, right? But it's something that if we get to do it, like, why not? Why not spend a slice of your time doing a high risk, high reward search of something for fun? So Professor Greaves actually decided to look for signs of life on Venus. And she actually read through the literature, and to her huge credit, she sorted through and came across phosphine. And she found the same papers that my team found, which described phosphine is found in mixed bacterial cultures, and the paper about the different oxygen-free environments on Earth where phosphine is found. And she proposed to use the James Clerk Maxwell Telescope to search for phosphine. And she got rejected, of course. The proposals were initially rejected. And she did it again, then was accepted. And she found a signal. And at that point, an independent person connected our two teams. And Jane invited us to join her team to search for phosphine and explain its presence. Well, when I first saw the data, I actually heard about this and saw it and talked about her with it. I was like, my reaction at first was like, well, the signal's not that strong, and I just don't see how there could be phosphine on Venus, because like Earth, Venus is oxidized. There's very little hydrogen. The conditions are not right, even inside volcanoes, to make phosphine. And it just seemed like I was quite confident that with better data that we wouldn't find phosphine. So we worked with Professor Greaves. We wrote a proposal to ALMA, which is shown on the bottom here. ALMA is this large, it's a millimeter array. It's a series of these dishes high in Chile in the high desert, because water vapor is really generally bad for astronomy. It's bad for these kind of measurements. I've never been there, and I don't know if they let visitors, but it's very high, something like 17 or 18,000 feet. And yeah, so there's about 60 different dishes here, and they all work together as an interferometer. So about Venus for a moment, due to a massive carbon dioxide greenhouse atmosphere, Venus's surface temperature is so hot. We hear it's hot enough to melt lead. No life could ever survive at the surface. Yet since Carl Sagan over half a century ago, people have been enthralled with this idea that there could be life on Venus, not on the surface, but high up in the atmosphere. Just like on Earth's atmosphere, it gets colder as you go away from the surface. And there's a layer in Venus's clouds that is not too hot, not too cold, but just right for life. Now, the clouds of Venus are very toxic. They're made of concentrated hydrosulfuric acid. So there's a sort of a set of challenges for life to be on Venus. But actually, there's also some mysteries that have been mysteries about Venus that have been there for a while, including that the pattern you can see on Venus here in this image, this is an ultraviolet image. And these big stripes are caused by an ultraviolet absorber. Actually, it's unknown what the compound is or why it's there. And it's the kind of thing that people like to speculate. Perhaps there's some sort of life form absorbing energy. So with all of this, we thought a lot about Venus. And there's one issue as well that's pretty critical. That is, how could life stay in the clouds of Venus? We're assuming life has to be inside the droplets, where there's a liquid environment and where life is protected from the very, very dry, incredibly dry conditions outside of the droplets. But the problem is that on Venus, the particles that are in the atmosphere, the droplets, they collide and they grow with time. So if you imagine like a life form, a bacterial type particle inside a cloud droplet, it will join with other droplets, but eventually these droplets get big enough, they're massive enough, so they fall out of the atmosphere due to gravitational settling. But if all life is, getting these droplets that are bigger and bigger and falls out, the question becomes like, how can life persist aloft? How can life stay up there like indefinitely? And it turns out, this is the one thing that I actually worked on in detail, because a lot of the work about life on Venus, it's very, let's say, qualitative rather than quantitative. And what I'm showing you here is a plot showing you altitude above the surface in kilometers and particle size, the particle radius in microns. And the contours and these dashed lines are showing you the time scale for different sized particles to stay in the atmosphere. So it's showing you that some particles, for example, let's say around a micron, can stay up for months in the atmosphere. And many of the particles are around that. And in Venus's atmosphere, particles don't fragment. They're not the right size, falling at the right velocity and such like that. So we came up with a hypothesis of how life could persist aloft indefinitely. And this is a cartoon diagram showing you from the Venus surface at 0 kilometer altitude up to 100 kilometer altitude, temperature and pressure scale on the right. But what you're supposed to look at here is there's this temperate zone in the clouds of Venus where it's the right temperature for life. And the idea is that as life would be in the particles and these particles fall out of the atmosphere, the liquid evaporates, leaving behind a dried out spore-like life particle. But once all the heavy liquid is gone, the spore can then float and remain in this kind of haze layer, which, by the way, there's this lower haze layer beneath the Venus clouds that it turns out that we don't really know much about it, why it's there. And the idea is that some of these spores might populate this layer. Anyway, there's a lot more to this. There's weaknesses and strengths of this hypothesis, but I just wanted to share with you that there's a bit of a renaissance with Venus, trying to take this idea that there might be life there a bit more seriously, and also trying to work out some more quantitative things about the atmosphere. So back to Venus and phosphine. Well, Professor Jane Greaves did find a signal of phosphine. And last September, the team made a big announcement saying that we have found phosphine in the clouds of Venus in the atmosphere, and stating that this is a huge mystery because it's hard to imagine how phosphine is formed. There must either be some unknown chemistry or possibly life production. And in terms of paths to make phosphine, we're not going to go into detail here. You're welcome to read the papers that the team has written on it. But essentially, you can kind of go through every possible way you can think of. Volcanoes, meteoritic delivery of phosphorus-bearing materials, lightning, surface minerals that get swept up and combined with water to make phosphine. But in each of these pathways, not a single one of them would generate enough phosphine to match the signal. And the signal is kind of at the level of part per billion. And some of these methods fall many, many orders of magnitude short. So now I'm going to tell you a bit about the data, which is, if you've been following this, you'll know that it's a highly controversial story. And I wanted to walk you through it for several different reasons. But one of them is as a kind of lessons learned for the search for life on exoplanets. Because Venus is right there, it's very bright. Exoplanets are very far away. And the kind of data that we're going to get in the future is going to be noisy data. It's going to be tough. So here's, yes.
Would you entertain questions during the talk?
Sure, if they're to the point for clarification, sure.
Yes. So Professor Yang Chen wanted to know, how did oxygen form on Venus?
We actually, you mean today, there's a tiny, tiny bit of oxygen. Like if he's asking about that, today people think they've seen a very, very small amount of oxygen, and people don't really know where it comes from. Yep. So back to this data, I should say up front that I am not a radio astronomer, but I'm going to explain this radio astronomy data to you the best that I can. What you're looking at in this image here is a plot. It says line to continuum ratio. So it's just data that's normalized here at 0. And on the bottom, you're seeing Venus rest frame velocity in kilometers per second. So if there's no absorption at all, this would be a straight line. And the bottom here, instead of showing you frequency or wavelength, what we would be used to, in radio astronomy, they're using a convention of showing it to you in velocity. So think of using Doppler shift to convert between wavelength and velocity. Now, Venus, by the way, it is heated by the sun, and its atmosphere is glowing in thermal emission. So it's just like on a day where the pavement is heated by our sun, it becomes really hot, or the really hot day, you can't walk outside in bare feet. So Venus is giving off thermal emission, even at radio wavelengths, even at millimeter wavelengths. So we're seeing thermal emission coming from Venus with an absorption line. And this absorption line is phosphine. It's a rotational transition of phosphine. And it's at 1.123 millimeters. So that's kind of the bigger picture of what this is. But I want you to know that the team found phosphine at 2 different observatories at comparable line depth, and using different techniques of data analysis that are relevant to each observatory. And interestingly enough, the data only showed this kind of consistent negative feature, like a drop here in absorption at the frequency of where we expect phosphine to be. So that's the sort of bigger picture encapsulation of where we were at last September. But in astronomy, we usually make our data public. It's either required by the telescope facility, or it's because we think it's the right thing to do. And this whole discovery, it created a lot of a big wave in the community. Like a lot of people were very angry, actually, which I'm not entirely sure why. But long story short is that people were able to look at the data and analyze their data on their own. And a number of people did not find a signal in the data. And specifically, they didn't like the way that our team had detrended the data. It turns out Venus, you'd think it's really easy to observe, but it's really almost too bright. It's too bright for our big facilities, and it's spatially resolved, which can create problems in this interferometer. And thanks to this expected scrutiny from the community, the team went back and looked at our data analysis processes. And before I get to what happened, in astronomy, if you use the Hubble Space Telescope, for example, and if you haven't used it, you can, because the Hubble Space Telescope, the people who work there, they usually calibrate the data. They do the first kind of level of data calibration. And in fact, all the big astronomy facilities do. The telescope that I was used to play a leadership role on, TESS, this MIT-led NASA mission, we provide calibrated data to the community. Now, you can go right to the most raw form of the data, but usually general observers actually don't do that. We trust the experts. Indeed, on our team, we had people from the ALMA Observatory. Well, the people from the ALMA Observatory went back and looked at how they calibrated the data, and they actually found a mistake in this. And this actually is not where you want to be. But it turns out that ALMA does not observe solar system objects very often. And they had a mistake in that the way they had 2 different modes of how to calibrate. They used actually one of Jupiter's moons, Callisto, and recalibrated the data and made the products public again. And I have to say that although we still find the phosphine signal in the ALMA data, it's actually much weaker. And we now just call it tentative. And what you're seeing on this plot is the same line to continuum ratio. And you're seeing the Venus rest frame velocity. And there are actually 2 different lines you're seeing here, this one in purple and this top one in blue. The one in purple is actually deuterated water, HDO. It's to show that we could recover a line that we expected to be there. But the top one is phosphine. And you have to, there's this line to guide your eye, but if you imagine that dotted line removed, you have to convince yourself that there's a drop in the signal right here where it's expected by phosphine. So the story actually continues that other members in the community have found a signal in the James Clerk Maxwell Telescope data. And they do find a signal there, and that's all good. But then people still want to argue away that it's not phosphine. They want to argue that it's the only other gas that is absorbing anywhere near the phosphine line is sulfur dioxide, which is present on Venus, but would have to be there in larger quantities than we've seen before by a factor of a few in order for it to have this line that overlaps here with phosphine. So before I leave the phosphine story, I just want to say the plot thickens a little because there's data from a probe that went to Venus, the Pioneer Venus, had a neutral gas mass spectrometer on it. And as the probe dropped down through the Venus atmosphere, it ionized gases and subjected them to magnetic field and measured the parent ions. And there's a paper actually that was just published recently describing how this Pioneer Venus data taken in the late 1970s actually supports the presence of phosphine gas. So this story is still unfolding. And it's a controversy that the team that I'm involved with really has to live every day. And I feel like for our lead, Professor Jane Greaves, it's literally a full-time job writing papers that respond to other papers in the field. But one thing I'll leave you with is that in terms of the chemistry of how phosphine might be made without life on Venus, with all the current understanding we have, actually there's no published paper on that yet. So no one has been able to come up with a way to make phosphine on Venus. So phosphine really is there. It's a huge mystery for us. So there's something really exciting happening now with Venus. And this sort of renewed interest in Venus has led me to lead a study of a mission to go to Venus. And I'm working together with Breakthrough Initiatives, sponsoring a mission. So we don't have a mission, it's a study that we've been doing. And this is to go to Venus on a small focused mission to search for signs of life and even life itself. And we're focusing on a small, medium, and large mission concept. And believe it or not, we're also orchestrating some biology experiments to understand survival of organics and signs of life that might be within the hydrosulfuric acid droplets. For example, there are people envision that perhaps some life forms have made a shell around them of a substance that's resistant to sulfuric acid, and just a bit of it. Yeah. So we do have some, I can't report on them yet, but there definitely is some progress in this area. So I'd like to give a shout out to two students here at Purdue, Rachna Agrawal and Weston Buchanan, who I'm just delighted to be working with. And they come out of Sarag Saikia's group. He's in India now, but he was at Purdue. And they work really hard on this mission on a huge number of variety of aspects. One of our mission concepts is to go with Rocket Lab. It's a small private commercial spaceflight rocket. It's a company that sends up small rockets. And their CEO, Peter Beck, apparently has always wanted to go to Venus and search for life. You can read about him saying that he's wanted to do this like his whole life. And so we've teamed up with them for our small mission. And the plan is that they will launch in May 2023 and will be responsible for the one small science instrument that can go on the payload. And we're working through that now. And our medium mission concept is for a balloon-borne platform that is inspired, like the one here you see at the bottom. It's in a museum. It's in the Air and Space Museum in DC. Actually, it's not in the Air and Space Museum, it's in the other center that's near the bigger airport. But in this case, you see this balloon with a gondola with some instruments. And the Russians sent 2 balloons to Venus in the late 1970s, and we're inspired by that idea, but we would have more sophisticated instrumentation. So that wraps up phosphine on Venus. And with all of that in mind, sort of the difficulty of getting a very small signal out of data, the sort of very uncomfortableness about phosphine being made by life on Venus, the whole thing about even having life on Venus, that's kind of a backdrop now as I move into talking about exoplanets. Now, exoplanets is a very, very interesting field that really just started in earnest about 25 years ago. We have so many planets now. These plots are capturing what we have today, showing you planet mass on a logarithmic scale as a function of orbital period in days, also on a logarithmic scale. And each of these different points is a planet. The different colors are just different planet finding techniques. On the right here, it's the same plot, but planet size instead of planet mass. I just want you to appreciate how many planets they are and how incredibly different they are, the widespread orders of magnitude in orbital period and mass and size. Actually, it's in mass. And it's just amazing to me that I just really always love to say that anything is possible for exoplanets within the laws of physics and chemistry. I mean, there are some planets that have periods that are less than 1 day. Some of these planets are so close to their star, the surface is hot enough to melt rock, and we imagine there are liquid lava lakes, not created by volcanoes, but just from the energy coming from the star. There's some planets that are like far bigger than Jupiter. We don't totally understand why. Now, you might want to read off patterns here and ask, oh, why are there patterns in this diagram? Some of these patterns are just selection effects. For example, ground-based surveys, it's easy to find big planets close to the star, and they're responsible for this big clump up here in the corner. But you can also see that where Earth and Venus are, where Earth is, the diagram is somewhat empty, actually. Remember, this is a log-log plot. So we're not quite there finding Earth twins yet. Now, when we think about the search for finding an Earth twin, it turns out that Earth is not necessarily the faintest object, like an Earth at 10 light years or 50 light years away. It's not really the faintest object that we've ever observed, like galaxies with the Hubble Space Telescope. The problem is that another Earth is right next to a big, bright, massive star, sun or star. In fact, our own Earth is 100 times smaller than our sun and 300,000 times less massive. And our Earth is 10 billion times fainter. Like if I was with you two in the room, I would ask for another show of hands. And I would ask you if you were going to take a sabbatical or take a shift in your career and start working on exoplanets, would you work on a technique that involves planet size? Because to find another Earth, your job is to make something work at the 1 part per 10,000, because we have to square it because it's the area that's important. Would you choose a method that involves planet mass? Because now your job would be to find a signal 1 part in 300,000 times. Because we can't separate that planet and star in these methods. We're looking at the planet's effect on the star. Or would you choose the hardest problem out there, which is trying to find an Earth in reflected light, where the Earth is 10 billion times fainter than our star? It's really interesting to think about physics and astronomy and which kind of experiments have had to work to that many decimal places. Like very, very few, right? Perhaps LIGO, perhaps a couple of others, but it's incredibly challenging. So if you voted for number one, searching for a planet with respect to the size, a technique that involves planet size, you would be with that most popular method today, which is transiting planets. Here you see a cartoon of the planet going in front of the star. Up here on the top, that's just an artist's conception. We haven't spatially resolved any stars at that level other than our sun. And on the bottom plot, you see what astronomers actually measure. It's a planet going in front of the star as seen from the telescope. And we can measure the planet brightness as a function of time, looking for a drop in brightness. Now, this actually is a very established field in astronomy right now. There are ground-based surveys. There's the TESS mission, and TESS looks at 20,000 stars at high cadence and like 1 million stars at longer cadence every month. And our computers search through the data and create a time series of the brightness of stars and then search for transiting planets. It's still really hard, though, to find an Earth. And so we've kind of taken even another shortcut, and that is searching for Earth-sized planets around very small stars. Here I'm showing you a real image of our sun, and I'm showing you a fake image of a small red dwarf star. This is supposed to resemble a famous star called TRAPPIST-1, which is literally among the smallest, coldest stars that exist. Any smaller and colder, and it would not be able to have fusion in its interior. So in the case of Earth, the Earth to Sun area ratio is 1 part in 10,000. But this Earth-sized planet around a small star, the ratio would only be 1 in 100. And the atmosphere, which I'll get to, is much more favorable as well for detection around a small star. So let me just take you on a really brief virtual trip to a planet around a red dwarf star, because I just wanted to kind of share with you how very different it is from, well, should be from our Earth. And the first thing you see in this, so let's imagine we can get on a spaceship and travel to an Earth-sized planet transiting one of these small dwarf stars. First of all, the artist has made the star or the sun really big in the sky. It might be, it might not be, but certainly for a planet as heated by the star to be the right temperature, not too hot, not too cold, but just right for life, the planet has to be quite close to the star because the red dwarf stars gives off very little energy. And the artist took the artist license here to make the atmosphere a different color, the sky red and the clouds purple, and is also showing you a couple of other planets. What I really like about this idea of visiting a red dwarf star is the fact that through tidal interaction over millions, billions of years, the planets are expected to be tidally locked. That is, they show the same face to the star at all times, just like our moon does to Earth. So that means that the planet rotates 1 time for every time it orbits the star. What this actually means, if we could visit the planet, is that one side would always be in day, and the other side would always be in night. So, where would you visit? Well, you'd probably visit, if you're an astronomer, you'd have to visit where it's always night. And the others, well, maybe we'd visit where the sun is always setting. Also, the year, the time it takes to go around the star, by Kepler's third law, objects that are closer to their star, depending on the mass of the star, orbit more quickly. And so a year on these ones is like 10 days, 20 days, 30 days. And on second thought, visiting this planet might be a really terrible idea because the red dwarf stars gives off flares, lots of high energy flares. In fact, some of you might have heard of this event here on Earth from, actually I'm getting a bit ahead of myself, but I'll come back to that story a bit later. Actually, no, I'll tell it now. Some of you might have heard of this event that happened here on Earth around the 1850s. It's called the Carrington event. And what happened was an amateur astronomer named Carrington in the UK was actually looking at sunspots and noticed that the sunspots in our sun brightened. And a day and a half later, our Earth became electrified. And what had happened was part of our sun had come off in a coronal mass ejection. And that part of the sun had a magnetic field embedded in it. And when it came hurtling towards Earth, this magnetic field hit our Earth's magnetic field and induced a current. And back then, Maxwell's laws weren't articulated. People didn't totally understand the connection between sunspots and magnetic fields. But our Earth became electrified such that apparently people could see the northern lights almost down to the equator. And here at the Indiana latitude, you would be able to go outside at night for that 1 or 2 nights and read a book by the brightness of the northern lights. And telegraph operators also saw their telegraph lines catch fire even. So we don't know if that's going to happen again here, but I want you to know on that TRAPPIST-1 star, it had been observed for about 80 days by the Kepler Space Telescope when it was looking at this field of view that included TRAPPIST-1. And astronomers counted 40 flares in that 80-day period, one of which they estimated was equivalent to our Carrington event. So some of these red dwarf stars, they're receiving lots of flares, and we don't know if that's going to cause the atmospheres to go away. We don't know if it's going to harm life. I mean, life is probably okay beneath an ocean or on the dark side or subsurface. But I just wanted to capture for you this tidal locking, the flares of the stars. It's really not like our Earth. What we're able to find right now in terms of Earth-sized planets around stars, we're not anywhere near being able to study a true Earth twin around a sun-like star. So yeah, just a bit more on these transiting planets. I mentioned NASA's TESS mission and just wanted to show you an artist's conception of the mission. In the top left here, that's an artist's conception. TESS consists of 4 kind of glorified telephoto lenses. Here's a small, tiny fraction of 1 small part of what TESS observes each month. And there's a corresponding beautiful transit down here. Now, what's so great about these transiting planets is they allow us to study the planet atmospheres. And before I can get to atmospheric biosignature gases on exoplanets, I have to do like a very brief tutorial here for you on this topic. So what you're seeing on the top is an artist's conception of a planet in front of a star, backlit by the star. And for those who work in this field or know what Beer's law is, that the intensity from the star gets exponentially attenuated by the molecules in the planet atmosphere. So effectively, you can think about it like the starlight shines through the atmosphere, and some of that starlight at specific wavelengths gets absorbed, depending on the gases in the planet atmosphere doing the absorbing. And if I just have like one takeaway for you here in this sort of educational part of the talk, which is how we think about and how we look for gases in exoplanet atmospheres. I want you to think about this transit at a wavelength where the atmosphere is transparent. So it's just the size of the planet and the area of the planet is just the dark part of the planet that you see here. So you'll have a certain drop in brightness. Now I want you to imagine observing the planet at a wavelength that is highly opaque. There's very, very strong absorption going on. Now the planet's a bit bigger because its diameter encapsulates not just the dark part of this planet, but this blue part as well, illustrating the atmosphere. So what we do is we think about it as looking for the planet changing in size with wavelength, where the planet is bigger at wavelengths where the atmosphere is absorbing. And just to remind some of you that each gas, it's kind of wrong to say it, but it's right to first order that each gas has a unique wavelength where it observes. And this is like a Wikipedia level picture of absorptivity, where it goes from 0 to 1 for different gases, showing you methane, nitrous oxide, oxygen and ozone, carbon dioxide, water vapor. That's what I want you to look at. Water is a very strongly absorbing gas. And right here where this red square is, it just so happened, like by chance in a way, that the Hubble Space Telescope has a very well-behaved detector on an instrument right at that wavelength. And that water vapor feature is one that we see on a good number of hot giant exoplanets. That's this same feature here. What you're looking at in this spectrum is transit depth. So this is the drop in brightness due to the planet and its atmosphere. And this is wavelength in microns. The white points with error bars are data from the Hubble Space Telescope. These ones over here are from Spitzer Space Telescope. And the solid lines are models, different models fitting the data. Now, if this planet had no atmospheric features, all we would see is a straight line. And I'm just guessing you can all agree with me that this is different from a straight line. And the fact that this feature here corresponds just right where water vapor strongly absorbs, we call this a detection of water vapor on this exoplanet atmosphere. Now, I actually did cherry pick like one of the best spectra for you, so you could see something that hopefully you all agree with and really like. And this drop in brightness, if you had time, you could read it off the y-axis, but it's about 1 part in 1,000. So today we can study giant planet atmospheres, hot atmospheres, puffy atmospheres, and we do that with the Hubble Space Telescope. Lots of people are in this community now and use Hubble to look for water vapor and other gases on exoplanet atmospheres. Very soon, we're going to use the same technique, and we're going to push down to small rocky exoplanet atmospheres using the James Webb Space Telescope. It is set to launch in October 2021. And it will take some time to get out to the Earth-Sun L2, a few months. And it'll take a few months to try the telescope out and commission it. And it's already slated to observe a lot of exoplanets, including the TRAPPIST exoplanets and many, many others. And we're going to, we meaning the whole community, will use this telescope to observe small planet atmospheres transiting, the planets transiting M-dwarf host stars. Now, I had one more little technical thing I wanted to share with you. I'm going to run out of time soon, but you know how I said before, we're doing the easy technique, transiting planets. We're making it even easier by transiting planets, transiting small stars. You know, we have one more kind of hope on this wish list, and that is that the atmospheres somehow, I don't know how, have hydrogen gas in them. that there are planets perhaps that are outgassing reduced materials. And I probably don't have time to go into this. This is like actually an exercise for an undergraduate kind of physics class, that you can estimate the size of the transit signal by literally calculating the annulus for this atmosphere against the backdrop of the star. You need the area of this annulus compared to the area of the star. And you can do this by assuming just for argument's sake, an isothermal atmosphere and taking hydrostatic equilibrium with the ideal gas law. If you just take those equations, do some algebra, you end up getting this pressure equation, that the pressure at Z above some surface is equal to the pressure at that surface exponentially attenuated, or rather, sorry, exponentially falling off. The pressure and the density drops off exponentially with height. And you know this sort of anecdotally from the climbers who go up Mount Everest. They always say they run out of oxygen, but they're running out of air. There's just less atmosphere up there. Well, this so-called scale height, the E folding factor for the drop in pressure and density as a function of altitude above the surface, it's related to the mean molecular weight of the atmosphere. And so if you think about a lightweight atmosphere like made of molecular hydrogen, compared to our Earth's atmosphere that's dominated by molecular nitrogen, actually the atmosphere will be way more puffy. So this sort of hydrogen atmosphere backdrop makes a bigger atmosphere. This area of the atmosphere compared to the area of the whole star is larger than compared to like our Earth's nitrogen atmosphere, which is fairly compressed in that picture. So by the way, if there is another Earth with Mount Everest and with a hydrogen atmosphere, then the hikers, the climbers, they can go up the mountain without running out of air. So we're not sure what is out there. A planet that could hold on to its hydrogen has to be colder or more massive and have continual replenishment of hydrogen from the inside. So that's kind of where we're at. And yeah, I had this funny cartoon because I was telling that story about how these M-dwarf stars, the small planets, they're very attractive to us, but we're not sure exactly what's going on with the atmospheres, with the stellar flares, and things like that. So for this last small section of my talk, I'm going to return to the search for biosignature gases on exoplanets, because now you're armed with some of the background about how we're going to be studying small exoplanet atmospheres with the James Webb Space Telescope and with the transmission spectroscopy technique. And it turns out that my team and a lot of other teams, we make these big computer simulations. And I always love this phrase for computer models is what you put in is what you get out. And so we have to spend a lot of time thinking about all the different scenarios that might exist on another planet. And specifically, we worry about photochemistry. We have a set of equations to describe the atmosphere. I've listed some of them here. They're all fine. They're all things you would expect to see in a applied physics problem. Conservation of energy, that's a good one. Energy transport, hydrostatic equilibrium, ideal gas law. The one that gets us though is photochemical equilibrium, because the gases we're interested in, we're hoping there's life there making the gas. There may be volcanoes making that same gas, but how those gases mix in the atmosphere and how long they last, it depends not only about the high energy radiation coming from the star, but it depends on a lot of things, like the rate at which gases fall out, whether or not there's an ocean. It depends on a lot of factors we just don't know. So I like to call it like the art and the science of exoplanets, because we have to think carefully through all the possibilities. And I'm sure when we're confronted with data, it'll be even more both interesting and messy. So one of the gases we like to simulate is phosphine. And you don't have to understand this whole plot. I was just sort of trying to show you, we make models, we generate fake spectra. This is transit depth in part per million. And this is wavelength in microns. And this green and purple are just showing you two different modes of the James Webb Space Telescope. And you're looking at two different spectra here, this white one and the blue one. And they're signaling, it's showing you one case with a huge amount of phosphine, a high production rate of phosphine, and one without. Just to sort of, you're supposed to see that we could imagine a world with a lot of gas being produced, just like a lot of oxygen is produced here on Earth, and creating a big spectral feature. So phosphine can accumulate in an exoplanet anoxic atmosphere. Phosphine doesn't appear to have false positives. in a planet with the temperatures and pressures suitable for a liquid water ocean. But we need a large production rate of phosphine. And one of the kind of conclusions that my group has been reaching, and it maybe sound totally obvious now, but we had to go through all the models to get here, is that we have to have other planets like Earth, where gas is being produced in very, very huge quantities. We're not saying that the atmosphere has to be completely re-engineered, like how oxygen filled our atmosphere to 20% by volume. But even accumulating enough of a biosignature gas on an exoplanet to find, it's not going to be like part per billion that we're claiming phosphine is at on Venus. It has to be like many, many, part per million, tens of part per million, 100 part per million, even in some cases a percent, which is really a huge amount. And this plot is showing you biological surface flux for some different gases. Don't worry about the units here, just notice it's on a logarithmic scale. And this orange color is the values, global values on Earth. So you see oxygen, there's quite a lot being produced, methane, ammonia, isoprene, tiny amounts of phosphine. And the blue is what we found for like ideal case exoplanets, that for the gases phosphine or isoprene or ammonia to be detectable, we need a huge amount being produced elsewhere. So we actually need these big production rates where the gases essentially saturate the sinks. They're produced in enough quantity to saturate or self-shield against destruction by usually photochemistry. And it's not just the James Webb Space Telescope we have to look forward to. There's large ground-based telescopes now under construction that are 20, 30, 40 meters in diameter. We have some very sophisticated concepts to go to space. And this one is showing you a giant star shade, a screen, specially shaped screen that would block out the starlight so we could see the planets directly and study atmospheres in a way different from the one that I've described. So to summarize my talk, the search for signs of life beyond Earth. We actually know that small rocky planets are common. As well, exoplanet atmosphere observations by transit spectroscopy are very well established for giant planets. So we are all set to go to, when the James Webb Space Telescope is launched, to study atmospheres of small planets transiting small stars, because the James Webb is just more capable and operates in the infrared compared to Hubble. We have this fast track for the search for habitable planets. That's why I described looking for planets transiting small stars rather than those transiting much larger stars like the sun. And finally, I went into a lot of detail on phosphine on Venus because there are lessons learned here. Then I also spoke to you about atmosphere simulations for the James Webb, where the James Webb represents our first capability as a community, as a scientific society, to search for signs of life on exoplanets beyond our solar system. That concludes my talk, and thank you for your attention. And we now will have some time for some questions.
How'd you like that?
Oh, I love that. That's great. Thank you.
We have a couple of questions. Actually, the first two are about your first half of your talk, specifically dealing with phosphine. So Jared Bland, one of our students, asked, he claims it's a somewhat naive question, but maybe not, because I think you somewhat described this. If humans can send a rover to the moon or Mars, why not send something to collect samples from the Venus atmosphere and see what is the UV absorber?
I love that question. And if you meet up with Weston, Rachana, they're actually helping, they're basically leading that part of the study, actually. And they will be able to answer this in a lot of detail. And I'd say we would love nothing more than to go to Venus, collect a sample of the atmosphere, the droplets, some gas, and bring it back here. So it's no such thing as a naive question. That happened to be a fantastic question. So I encourage you to meet up with the other student, like for details. If you want to know the detail, we're still working out, like how much can we bring back? What would the mission look like? Because you can't fly deep in the atmosphere where the clouds are and come back. Like you're just not going to have enough. You have to imagine like perhaps a balloon platform that's floating around capturing stuff that has like a rocket attached to it that can send it back up to meet an orbiter to go back to Earth. So we haven't done it because it's so complicated. But yes, if we gave enough time and attention and money, we could solve this.
James Haber from EAPS grad student asks, is phosphine detectable in exoplanet atmospheres?
is phosphine detectable in exoplanet atmospheres? As a sign of life, it's going to be incredibly hard to do, actually. And so far, you know, when you think about phosphine, for hydrogen-dominated like giant planets, let me think for a moment. Like it actually might be detectable in giant planets because they have a lot of hydrogen. Like our Jupiter and Saturn have phosphine because they have a lot of hydrogen, and beneath the atmosphere, it's very hot. The temperatures and pressures, you know, favor phosphine being the dominant form of phosphorus. So yet, probably yes for giant planets, and it'll be really tough to find it. It's still one of our favorite biosignature gases, but it'll be tough to find it on a small exoplanet.
Someone named GC, or labeled GC, asks, do we know how often Carrington events occur here on Earth?
Oh, that's a great question. We do not know how often they are here on Earth. Just, I want to answer a slightly different question. I always tell my students not to do that, but I first want to say, with the TESS data, you know, TESS has observed now millions and millions of stars for 1 month, you know, each or more, because now we've looked at most of the night sky and now we're looking at it again. And one of the postdocs at MIT, his name's Max Gunther, he has tabulated how often Carrington events occur on other stars, on some of these M-dwarf stars. And some of them, a Carrington event is coming off the star like once a week or something crazy like that. You know, for our Earth, you hear the phrase like every 150 years. But I don't know if that's just meant to scare us because that means we're due for one now. But I really don't think we know. And don't forget that the sun will give off something off in all directions. So Earth has to be in the line of fire as well. And I don't think we've seen a Carrington level event go off in another direction. However, some of you, I know there's some people here because they're from Canada like I am, and they're about my same age. You'll remember in the late 1980s, we had a miniature Carrington event. If I could see them, I know they'd be nodding. And this miniature Carrington event knocked out some of our satellites, actually. Yeah, so the answer is we don't know for Earth, but we'll wait and see. If it does happen, you'll know, because most likely our power grid will get knocked out and we'll be in pretty big trouble. I'm saying that with a smile, but it could be a really big problem for us today.
Right. Jared Bland, one of our students, has asked, is a magnetosphere uncommon? If a planet was near the TRAPPIST star during a Carrington type event and the planet also had a protected magnetosphere, would it be so devastating to surface life? I think,
you know, to me anyway, the jury's out about whether or not it will hurt surface life. I don't know really. Even high energy particles like life. I just want to say this. I always imagine it like here. Does this happen to you in Indiana where you can get a snow day? Does that happen? Do you get so much snow that they'll just shut everything down for a day? I'm looking at John. He didn't say it, but
pretty rare.
Oh, okay. It happens here pretty often. Like some years here in the Boston area, we'd have like 5 days, 5 separate days, you know, would be a snow day. You get so much snow. I always imagine that if you lived on a planet like that, you'd have time because you could monitor your star. You'd see the event happen. You'd have some time before it hits your planet. And maybe you'd have a like, okay, everyone, you're staying home, you're staying in your basement. But yeah, so the question is magnetosphere. We don't know if other planets have magnetic fields actually. And we don't know if there's like liquid on the inside of a planet that could generate a magnetic field. We don't, you know, we're trying to understand interiors of planets, but more planets more massive than Earth, they have higher pressures on the inside. And we need more attention for people to figure that out. We can't really measure these. I don't mean to make it so negative. It is a really good question because we can't measure magnetic fields on things far away. We don't have a way to do that. So we're really, really not sure actually. But possibly by looking at whether the planets have atmospheres or not, we'll have an idea about whether they have magnetic fields. Not really sure. But I don't think it would be a huge problem for life. I think life could exist beneath the surface, beneath an ocean, something like that.
Okay. GC has another question. How long does it take to collect light for one of these typical absorption spectra?
For exoplanets, for these transiting planets, for a hot giant planet, let's say you're using Hubble, you might just take one transit. So you'd actually bin the data from the whole transit. And if the transit, let's say, lasts a few hours, and then you get equal amount of time out of transit to compare it to. So let's say 6 hours. But for these small planets, you know, remember, you're thinking of that image of the annulus of the atmosphere compared to the whole star. That really small atmosphere, you know, like the skin of an onion on an onion. It could take you 10 transits. It could take 20 transits, or maybe even more actually. And so for some of the planets we want to observe, we're not sure if we can convince the telescope allocation committee that a given planet deserves that much time. So actually the whole thing varies. Big hot planets, it's not a problem, say 6 hours or 12 hours. But for these small planets, it could take many, many transits.
A question from Colin Hamill, who's an EAPS grad. How will exoplanet clouds impact your ability to detect biosignature gases?
Clouds do turn out to be a problem in general. When there's clouds, many exoplanet atmosphere spectra that the community has looked at, they do show a perfectly straight line, actually. Not perfectly straight, but within the noise. And we know that these giant planets have atmospheres by definition because they're primarily hydrogen and helium. We know that based on the planet's average density. So clouds can completely block those rays coming from the star, actually. They can block the rays so much that the spectral features are much weakened. That's like, I'll say like when we used to go on airplanes, and if you fly through the clouds block off everything beneath you. In fact, they're blocking off the part of the atmosphere where the spectral lines are formed, the deeper part. So yeah, they could really mute the signal. Oh wait, all that said, we're hoping that at like infrared wavelengths, the clouds are penetrable. We're hoping that the clouds won't block everything everywhere, but we'll have to wait and see.
2 more questions. This one's from Shiva Kanakanchi, who's a grad in our department. Can phosphine serve as the signature of life on a planet, even in the absence of any water on the planet?
Yeah, that's a good question. Well, we think that all life needs some kind of liquid. We like water because it's got a large temperature and pressure range where water can be liquid. And most of the planets we can detect, they're not really cold things like Titan. So water is a natural one, but I do think that we'd have to have evidence of some kind of liquid. But think about Venus, for example. There's almost no water in Venus's atmosphere. It's so dry. It's like far drier than the driest place on Earth. And there we're imagining a different type of liquid, like sulfuric acid droplets as being a liquid where chemical reactions can happen. So thinking through it that way, the answer has to be yes.
Okay, very good. The last question is from Stephanie Olson, who's a professor in EAPS. Are volcanoes, meteors, lightning, surface minerals better at making phosphine on reducing planets? And what sort of observational context could we use to identify or reject false positives?
So if the planet does have a lot of hydrogen, then all these different methods would make it easier to generate phosphine. But still, don't forget what I said before, that at the temperatures and pressures where water can be liquid, if you need water, then phosphine just still really doesn't want to form, Phosphorus wants to be with oxygen and phosphates. So I think it would be easier, but I don't know if it would really solve your problem. And about false positives, for exoplanets, it's going to be really tricky. Like I would have said before, that's why my slide said phosphine, no false positives. But for exoplanets, we don't really have enough information. So it could be really challenging to ever really know that a gas is uniquely produced by life on another planet.
Okay, thank you. And Matt Lister just wanted to note that his family had a cottage in Quebec during that event.
Oh, wow. That's interesting, yeah.
So let's thank Sara again for a wonderful talk. And it was a great presentation. I'm going to put away my clapping effect. Is Dave Cederberg online, or do I stop the live stream? I guess I stopped the live